Going to continue with chapter 25, talking about galaxies. This time we're going to talk about our historical attempts to determine the mass of the galaxy and start talking about why galaxy rotation hints at dark matter. We won't really look at dark matter until chapter 28, but we're getting there. And it's interesting how we started at the moon and then solar systems and stars and now galaxies and the universe. And the farther we go through the course, the more we are getting into the cutting edge of physics and astronomy research, because it's the stuff way out there that we still just do not understand. So, Kepler. Remember Kepler? I told you that we would spend a whole lot of time this semester talking about Kepler, and you said, okay, cool, and now here we are. This is what, the third time that we've talked about Kepler? And that's because he was such a visionary about his understanding of how something orbits something else. Those laws, a cubed equals p squared, work for galactic motion. So the amount of time it takes something to go around a bigger something is related to how far apart those two things are. And this works for atoms, for moons, for planets orbiting a star, for stars orbiting the center of a galaxy. This works for galactic clusters. It's amazing. So, when we are looking out into the Milky Way and we watch clumps of gas as they orbit around the center of our galaxy, if our galaxy were, only about 28 or 30 light years across, like, if we were at the edge of the galaxy, then this rotation curve would curve down as we get out from the galaxy. So what is this rotation curve anyway, right? So when we are watching clumps of gas orbit around the center of the galaxy, the clumps in the very center don't orbit. You move out just a bit and all of a sudden they're orbiting very fast. And we see this curve move along, but if we were at the edge of the galaxy, the clumps farther out would slow down. Remember Kepler again. What did he say about objects closer to the center of mass? They move faster. But galaxies don't follow that rule. We're going to talk about this later. And for our Milky Way, it continues increasing in orbital velocity, which means that there is a lot of stuff beyond the sun in our galaxy. So dark matter is, an undetected at this point form of mass, emits little or no light. So there are several options for what dark matter could be. At the moment, the name dark matter is a placeholder for something that we're just not sure what it is yet. Dark energy is the, unknown form of energy that is pushing out, causing the universe to expand. We know that neutron degeneracy pressure pushes out on the core of a neutron star, refusing to allow that star to collapse. We can't see it, but we know that it's there because we have studied neutrons and we know that they don't want to touch, and we know that that star is full of neutrons. So neutron degeneracy pressure is there. Dark energy is the pressure pushing out on the universe. We can't see it, but we know it's there. And so we will talk about the possibilities for both of those. So what is the evidence for dark matter? We're not going to do anything more today than just, I'm going to show you the 4 lines of evidence. We'll talk about each of them individually in chapter 28. So the rotation curve of galaxies, I just showed you that rotation curve for the Milky Way, explaining that there is a lot more outside the orbit of the sun than there is inside the orbit of the sun. The speed of orbiting galaxies in galaxy clusters. So where you have 5 or 6 galaxies clustered together and they're orbiting around, each other. The large amounts of X-ray emitting hot gas in galaxy clusters. So X-ray emitting hot gas is a thing. It is hot gas. It is gas that is so hot that it emits X-rays. And then gravitational lensing, which is really cool. But we'll talk all about all of that more. Radio and X-ray observations that help us understand what's going on in the center of our galaxy. We're going to talk about those. So, the galactic central region. This is a radio map. This image is a radio map of the center of the galaxy. It was constructed from data from the VLA, the Very Large Array in Socorro, New Mexico. If you ever get a chance, you should go. It's really cool looking. And so bright regions give off more intense radio waves. And so the galactic center is in this region labeled Sagittarius A. B and B1 and B2 are star-forming regions. And then we see a bunch of bubbles that are supernova remnants. So just cool. So why is the galaxy, the center of the galaxy, so hot that the gases emit X-ray? I mean, we're not very hot. We emit, infrared. And then you get hotter and there's visible light, and you get hotter and hotter, and you finally get to X-ray. So the central portion of our galaxy is so hot that the gases give off this haze. So we have the tiny dots of light that are individual white dwarfs, but the haze is different. And then some interesting things to note. The red is the low band of radio energy. The green here and here are medium band. The blue are separated. And so when we get up to chapter 28 and we're talking about dark matter and dark energy, we're going to explain why the hottest portions of the galactic center are actually not at the galactic center. Another picture of the galactic center of the Milky Way, Sagittarius A star. That's how that's said. And yes, Sagittarius A star is not a star. But I'm getting ahead of myself. So we have these streams of hot gas that are being thrown out of the Sagittarius A star region. And so let's look in even closer. If we look at the tracks of stars orbiting the center, this is an image created showing the location of stars over the period from 1995 to 2014. So if we look here, when a star is farther from the center, it is moving slower. So from one dot to the next dot is a year. So from 1995 to 1996, not much move. From 2013 to 2014, a huge movement. So that helps us see that we're going to go back to, you guessed it, Kepler. When an object is closer to the center of mass, it moves faster. So we can see that on the very elliptical orbits, they swing around this. Well, there's nothing there. There's bound to be something there. The very round orbits have less of a change in the speed, but that's to be expected because they are not very elliptical. They are much more circular. But all of these are moving around a single massive gravitational force. So Andrea Ghez and her team are the ones who did all of that research. Right down here is the URL for a YouTube video. It's really cool. You should go and watch it just because, well, it's interesting. But they made massive leaps in our understanding of the fact that Sagittarius A star, it's not a star. It's a black hole, a supermassive black hole. So, oh, and that is my reminder to stop recording because I tend to make the videos too long because I just forget and keep talking. So, in a minute, we will finish out chapter 25.